Welcome to the Deep Dive, the show where we unpack complex topics to give you clear, actionable insights. Today we're tackling a big one, a question you often see in senior DevOps and cloud engineering interviews. How do you scale GitHub Actions for, let's say, a massive 10,000 builds every single day? And it's definitely not just about, throwing more compute at the problem. It's really about smart infrastructure strategy.
That's exactly it.
Yeah.
Yeah, 10,000 builds a day, you're talking hundreds of builds running at the same time, especially during peak hours.
Yeah.
That pushes way past the standard GitHub limits. So our goal here is to really explore the different paths you can take, balancing the trade-offs, cost, how complex it is to run, and maybe most importantly, how it impacts your developers.
Right. And we're going to break this down into three main ways to tackle it. First, using GitHub's own larger runners. Second, self-hosted runners, specifically with the Actions Runner Controller, or ARC. And third, the super optimized Kubernetes executor model.
Okay, so before we jump into the solutions, let's just quickly nail down what 10,000 daily builds actually feels like operationally. It sounds huge, but what does it mean day to day?
Yeah, it's a good place to start. At enterprise scale, 10,000 builds a day, if you assume they're mostly happening in an 8-hour workday, you're looking at something like 420 concurrent builds running during your busiest times.
420, okay.
Right. And that immediately tells you standard GitHub runners aren't going to cut it. Not even close. So the real challenge isn't just getting enough machines, it's making those fundamental architectural choices. How much do you value cost savings versus, say, operational ease or developer speed? Each option we'll discuss kind of represents a different philosophy on where you invest your engineering effort.
Gotcha. So for you listening, thinking about that interview question, the first really critical thing is to show you understand the scale itself and what problems that scale creates. It's not just jumping to an answer.
Exactly. Understanding the why behind the problem. All right, let's dig into that first approach then. Using GitHub's own larger runners. What's the quick pitch for this one? Why is it attractive?
Okay, so this is what I call the premium simplicity option. GitHub's larger runners, especially on enterprise plans, they can handle up to 1,000 concurrent jobs. So on paper, that covers your 10,000 daily builds, right?
Mm-hmm.
The big sell here is speed to value. You can basically turn them on and go with almost zero engineering overhead for your platform team. Now, GitHub offers different sizes. You've got 4-core, 8-core, 16-core Linux runners, and others too. A 4-core, for instance, gives you 4 virtual CPUs and 16 gigs of RAM. The cost is per minute, around 0.008 times per minute for that 4-core runner. More cores, more RAM, higher cost. Makes sense.
Okay.
But the really interesting part, especially for an enterprise thinking strategically, is what you don't see. The hidden operational benefits. GitHub manages everything underneath. We're talking OS patching, security updates, setting up the runners, cleaning them up after, network security, compliance checks, even dealing with hardware failures. They handle all of that. And what that really means is your platform engineers. They can focus purely on delivering features, on product innovation, instead of managing CI/CD plumbing.
That's a huge point, the undifferentiated heavy lifting, as they say.
Exactly. Now let's hit the cost piece, because that per minute rate adds up. If you have 10,000 builds, and let's say they average 15 minutes each on those 4-core runners, you're looking at roughly $18,000 a month.
18,000. Okay, that's not trivial.
No, it's not. That's 150,000 minutes times that 0.008 rate. But here's the cost justification argument you need to make. You compare that $18 T a month to the cost of not needing maybe 1 or 2 dedicated platform engineers just to manage self-hosted runners. You could easily be saving, say, $200,000 or more in annual salaries right there.
Yeah, okay. So you're trading direct infrastructure cost for engineering focus and speed.
Precisely. You're buying back engineering time. You're accelerating your product roadmap. That's the value proposition.
So boiling that down, what are the key takeaways for this GitHub-hosted option if you were summarizing it in an interview?
Okay, key takeaways for GitHub larger runners. 1, simplicity and speed. You get value almost instantly. Minimal operational fuss. 2, it's a managed service. GitHub handles all the underlying infra, security maintenance. Big win there. 3, cost justification. Yes, the sticker price seems high, maybe $18K a month for our example, but you offset that potentially by saving $200K plus a year in engineering salaries. You have to frame it that way. And 4, concurrency. Up to 1,000 concurrent jobs on enterprise plans so it can handle the theoretical load.
Okay, that's very clear. Simple, fast, managed, potentially justifiable cost if you value engineering time highly. So when would you strongly recommend this, and what's the trigger to maybe look at self-hosting instead?
It's perfect for teams that really prioritize speed to market, like startups, or maybe teams doing rapid prototyping. Anywhere that operational burden is a major distraction, the trigger to look elsewhere, usually it's either the direct cost becoming just too large to ignore at massive scale, even with the engineering savings factored in, or maybe you hit very specific compliance needs or need deep customization that the managed service just doesn't offer.
Gotcha. That makes perfect sense. Okay, so if those triggers hit, you start looking at self-hosting. Let's talk about option 2. Self-hosted runners with the Actions Runner Controller, ARC. How does ARC change the self-hosting picture? What's different about it?
ARC is a game changer for self-hosting, really. It takes the old model of having like static virtual machines sitting around waiting for jobs.
Right, the always-on runners.
Exactly. And it turns them into dynamic auto-scaling workloads running natively inside your Kubernetes cluster.
Wow.
This gives you way more control and honestly opens up some serious cost optimization plays.
Okay, Kubernetes native. So how does it actually work? What are the pieces?
All right, let's break down the ARC architecture. There are basically 3 main parts. First, you've got the controller manager. Think of it as the brain. It's constantly polling the GitHub API, looking for jobs, waiting in the queue. Second, you have runner scale sets. These are essentially Kubernetes deployments that ARC manages. They automatically scale up or down based on how many jobs are waiting.
Ah, so it spins up runners only when needed.
Precisely. And those runners are the third part, the runner pods. These are temporary, ephemeral containers that pop up, run a single job, and then disappear. And the beauty is you control this. You can set things like max runners, maybe you cap it at 500 concurrent pods. You can specify your own custom runner image, like my registry custom -runner.latest, maybe with all your build tools pre-baked.
Oh, nice. Faster builds.
Potentially, yeah.
Yeah.
And you define the resources too, like maybe you need 2 CPUs and 4 gigs of memory for typical builds. You set those requests.
Okay, so fine-grained control. What about the scaling speed? How quickly can it react?
It's pretty quick. Scale-up time for a new pod is usually somewhere between 30 and 90 seconds, and sail down is immediate. As soon as the job finishes, the pod terminates.
That sounds efficient.
It is. Your maximum concurrency is basically just limited by how big your Kubernetes cluster is. One small caveat, though. GitHub does have a limit on how fast you can register new runners. It's about 1,500 runners every 5 minutes for the whole organization. Something to keep in mind if you have really spiky loads.
Okay, 1,500 per 5 minutes. Got it. Now, you mentioned cost optimization. How does ARC help there? That's usually the main driver for self-hosting.
Absolutely. This is where ARC really shines. The biggest lever is spot instance integration.
The cheap compute.
Exactly. By using standard Kubernetes features like node selectors and tolerations, you can tell ARC to schedule runner pods onto spot instances whenever possible. The savings can be massive. We're talking 60, maybe even 80% reduction compared to on-demand prices.
Wow, okay, 60, 80%. That's huge.
It really is. And beyond Spot, you also get custom hardware matching. Got a build that needs tons of CPU. Schedule it onto a compute-optimized node pool, memory hog. Use a memory-optimized pool, need GPUs for some ML task, spin up a GPU node pool just for those jobs. You match the hardware to the job so you're not overpaying for resources you don't need.
That level of control is impressive. But it sounds like there must be some sharp edges, some gotchas when you run this in production.
Oh, definitely. With great power comes, well, operational complexity. First big one, runner group limits. GitHub limits you to 10,000 runners per runner group.
Okay.
For our 10,000 daily build scenario, hitting peak concurrency, you'll likely need to split your runners into multiple groups, maybe like build runners, test runners, deploy runners. Each might have different instance types or scaling rules. Need some architecture thought.
Right, segmenting the work.
Yeah.
Exactly. Second potential headache, GitHub API rate limiting. ARC hits the GitHub API a lot to check for jobs. You need to monitor those limits carefully. Installation tokens usually get you 5,000 to 15,000 requests per hour, depends on your plan. But the standard GitHub token inside a job, that's only 1,000 per hour per repo. We actually had a situation once where a team running ARC hit that API limit hard. Their entire CI pipeline just stopped, dead in the water for an hour until the limit reset.
Ouch. Lesson learned.
Yeah, a painful one. So monitoring those API calls is absolutely non-negotiable. And finally, just the standard network and security stuff. You need proper VPC setup if runners need to talk to internal services, tight security group rules, image scanning for your custom runner images, all that good stuff.
So summarizing ARC, what are the key takeaways for an interview answer? Okay, for ARC, 1, it's Kubernetes native control. Dynamic auto-scaling runners right on your own cluster. 2, significant cost savings, mainly through spot instances that 60–80% potential plus hardware matching. 3, increased customization, full control over the runner image environment, the underlying nodes. 4, Higher operational complexity, definitely need Kubernetes skills and careful monitoring of those limits and security. And 5, scalability. It's highly scalable, pretty much just limited by your cluster size and budget.
Makes sense. More control, potential for big savings, but you take on the operational burden. So where do teams usually stumble when they adopt ARC? Is it mostly the Kubernetes part?
Yeah, often it's underestimating the Kubernetes expertise needed. It's not just deploying ARC itself, but managing the cluster day to day, troubleshooting weird network issues, optimizing node pools, getting resource requests and limits just right.
Right, tuning it.
It's exactly. Teams often struggle there initially. They either over-provision, wasting money, or under-provision, leading to slow or failing builds. The way you really weigh the burden versus the benefit is a solid total cost of ownership calculation. If the compute savings significantly outweigh the cost of hiring or training platform engineers, and you need that customization or compliance control, then ARC starts looking very attractive.
Got it. Okay, that sets the stage nicely for our third option, which you flagged as potentially the most efficient, but also the most complex, the Kubernetes executor model.
Yeah.
How is this fundamentally different from ARC, and why go down this road?
Right, the Kubernetes executor model, it's a different philosophy altogether, popularized by GitLab, actually. Unlike ARC, which uses runner-pods that might stick around a little between jobs depending on configuration, the Kubernetes executor creates a brand new, dedicated pod for every single build job.
One pod, one job. That's it.
Exactly, one pod per job. And this leads to the ultimate efficiency, really strong isolation, and enhanced security.
Okay, how does that pod per job change things?
Well, first, perfect resource isolation. Jobs can't interfere with each other because they're in completely separate pods, separate environments. Second, zero idle costs. The pod spins up, runs the job, and terminates immediately. No runner sitting idle waiting for work. That eliminates a huge chunk of wasted compute in traditional CI.
Ah, okay. That's a big deal.
Huge. Third, unlimited scalability in theory again, just limited by your cluster capacity. And fourth, enhanced security, because every single build gets a completely fresh, clean, disposable environment. No leftover state or potential vulnerabilities from previous jobs.
That sounds amazing, especially the efficiency and isolation. But you said GitHub Actions doesn't support this natively, so how do you implement it?
Correct. It's not an out-of-the-box feature with GitHub Actions like it is with GitLab Runner. You have to build it. Typically, this involves creating a custom webhook handler. This service listens for specific GitHub Actions job events, like workflow job queued. When it receives an event, it dynamically creates a Kubernetes job resource. This Kubernetes job then specifies a container image, maybe something like runner with actions, that knows how to execute the action steps. Crucially, your webhook handler injects the necessary context, like the GitHub token and other environment variables, into that job pod dynamically.
Okay, so custom tooling required, a webhook listener, and something to create K8's jobs.
Exactly. And where this model really excels is in advanced resource management. Because you're creating a pod per job, you can define very precise CPU and memory requests and limits tailored to that specific job. This gets even more powerful when you combine it with what we call a build classification system.
Build classification, what's that?
It's where you categorize your builds based on their typical resource needs. For example, small builds like linting or unit test, maybe they only need half a CPU and a gig of RAM. Medium build integration test, maybe 2 CPUs, 4 gigs RAM. Large builds like a full application compile or end-to-end test, maybe they need 8 CPUs and 16 gigs. Your webhook handler looks at the job type and applies the right resource profile when creating the Kubernetes job.
Wow, okay, that's incredibly fine-grained. So what does this do for cost efficiency?
This is where you see dramatic results.
Yeah.
By eliminating that idle runner time completely and by right-sizing resources for every single job, you can push resource utilization incredibly high. We're talking potentially 85 to 95% utilization. Compare that to maybe 30 to 50% you might see with persistent runners, even auto-scaled ones.
85 to 95%, that's huge.
It is. And that translates directly into cost savings. You could see cost reductions of 20 to 70% compared to even an optimized ARC setup doing the same workload. Plus, you get true instant scale to zero. If no builds are running, you're paying practically nothing for compute.
Okay, that 85-95% utilization, the 40-70% savings, it sounds almost too good. What's the catch? Is this actually realistic for most companies, or is this just for, like, the tech giants with massive platform teams?
That's the right question. It is realistic, but the catch is absolutely the custom implementation. It requires a significant upfront engineering investment. You need to build and maintain that webhook handler, the custom runner logic, the build classification system. It's not trivial.
Right, it's a product in itself, almost.
Pretty much. So for many organizations, that high operational complexity and initial engineering effort might just not be worth it unless their scale is truly enormous or their cost per build is an absolutely critical business driver. It's definitely more common in larger, mature tech companies with dedicated platform engineering teams whose whole job is optimizing CI/CD infrastructure.
Okay, that context is crucial. So, Kubernetes executor, peak efficiency, ultimate isolation, but requires serious custom engineering. Let's pull back a bit. We've looked at GitHub larger runners, ARC self-hosted, and this custom Kubernetes executor. Each has clear pros and cons. Now, the million-dollar question, especially for an interview, how do you actually choose the right approach? And how do you roll it out successfully in a large organization?
Right, the decision process. You absolutely need a structured framework. It's not just gut feel. You need to evaluate each option against key dimensions. Things like operational complexity, how hard is it to run? Cost efficiency, what's the total cost? Customization, how much control do you need? Security isolation, how separate are the builds? And time to market, how fast can you get it working?
Okay, like a decision matrix.
Exactly. And if you were to sketch that out very roughly, GitHub, larger runners. 5 stars for low operational complexity and fast time to market. Maybe 2 stars for cost efficiency because it's pricey. ARC, self-hosted. Maybe 3 stars for operational complexity. It's manageable but needs work. 4 stars for cost efficiency, good savings potential. 3 stars for time to market, takes weeks, not days. Kubernetes executor. 1 star for operational complexity, it's high. 5 stars for cost efficiency, best in class. But only 1 star for time to market, this takes months of effort.
That's a helpful, quick comparison. So how do you apply that based on what you're actually building?
You tailor it to the workload. If you have tons of high-frequency, relatively simple builds where cost is paramount, that custom Kubernetes executor, despite the effort, might be the best long-term play for maximum efficiency. For a typical mixed workload enterprise doing lots of different things, a hybrid approach often makes the most sense.
Hybrid, using multiple types.
Yeah. Use GitHub larger runners for those critical paths where you need sub-minute queue times and instant feedback. Pay the premium there. But for the bulk of your builds, the less time-sensitive ones, route those to ARC self-hosted runners, running on spot instances for cost savings.
Okay, route based on need. That sounds smart.
And if you're a startup or doing rapid prototyping, stick with the GitHub-hosted larger runners initially. Zero operational overhead lets you focus 100% on your product. You can always optimize later.
Okay, that makes sense. Now, let's say you've chosen maybe that hybrid ARC plus larger runners approach. How do you actually implement that at a big company without breaking everything?
Phased approach, absolutely critical. You don't just flip a switch for 10,000 builds a day. I usually recommend a 3-phase strategy over, say, 12 weeks. Phase 1, foundation, weeks 1 to 4. First, get your baseline metrics. What are your current build times, costs, failure rates? You need numbers.
Well, sure.
Always. Then, deploy a pilot ARC infrastructure. Start small, maybe aim for 100 concurrent runners. Get monitoring in place. Prometheus for runner stats is common. And set up robust cost tracking. Tag everything.
Okay, foundation laid, then what?
Phase 2, scale testing, weeks 5 to 8. Now you start gradually migrating traffic. Don't do it all at once. Maybe 10% of builds go to ARC first. Watch closely. Then 50%. Then 90%.
Okay, incremental rollout.
Yeah, and during this phase, you focus heavily on performance tuning, adjusting scaling parameters, resource requests. You also harden security network policies, image scanning, secrets management, and think about disaster recovery, multi-AZ deployment, backups.
Building confidence and stability.
Exactly. Then phase 3, advanced optimization, weeks 9 to 12 and ongoing. Now you get sophisticated. Implement that intelligent routing I mentioned. Send builds to the right runner type based on rules. Create custom runner images optimized for specific tech stacks, maybe smaller images, faster startup. Look into advanced autoscaling, maybe predictive scaling based on historical load, and fully integrate spot instances, making sure your setup handles interruptions gracefully.
So constantly refining.
Continuously. And throughout all these phases, you need to be tracking key metrics religiously. Performance, queue time, execution time, success rate, economics, cost per build, resource utilization, engineering overhead, operations, stealing speed, failure types, security incidents.
That's a really solid playbook. Why is that phased approach so vital? Why not just aim for the final state faster?
It's all about risk reduction, really. You're making a major infrastructure change. Doing it incrementally lets you gain operational experience, learn the system's quirks, validate your cost assumptions, and build trust with your developers. If you try to jump straight to the most complex end state on day one for thousands of builds, you're just asking for trouble. Burnout, outages, missed deadlines. A phased approach delivers value steadily and keeps things stable.
De-risking the whole process makes total sense.
And building on that foundation, especially at enterprise scale, there are other advanced patterns to consider. Things like multi-region deployment, spreading your runners across different AWS regions or Azure regions for resilience and maybe better performance for global teams.
Right, fault tolerance.
Exactly. Also, build pipeline optimization, using features like parallel job matrices and GitHub Actions to split up huge test suites. Implementing smart dependency caching, maybe using shared persistent volumes, optimizing how large build artifacts are handled, maybe routing them over internal networks instead of out to S3 and back.
Squeezing out more performance.
Yep. And finally, compliance and governance. This is huge in regulated industries. Things like ensuring you have detailed audit logs of all runner activity going to your central SIEM system, setting up strict network isolation, maybe separate VPCs for runners handling sensitive production deployments, integrating securely with enterprise secrets management tools like HashiCorp Vault or AWS Secrets Manager.
Okay, lots to consider beyond just the runners themselves. Now, let's talk ROI. You mentioned costs earlier, but can we put some rough annual numbers on these options for that 10K build stay scenario?
Yeah, let's look at the annual total cost of ownership, rough numbers, of course. GitHub-hosted larger runners. Purely infrastructure cost. Based on our earlier estimate, that's around $18,000 a month, so roughly $216,000 annually. Remember, zero platform engineering cost for management assumed there.
Okay, 216K.
ARC self-hosted on AWS, say. Now you have compute costs. Hopefully lots of spot, storage, and networking. Plus you need some engineering time to manage it. Let's estimate maybe half a person, half an FTE. The total might come in around $175,000 annually. So maybe a 19% saving compared to GitHub hosted, give or take.
Okay, decent savings, but you need that half FTE.
Right. Now the Kubernetes executor, custom build. The compute cost here could be incredibly low due to that high utilization, maybe only $65,000 annually. But you need significant engineering effort, likely at least one full-time engineer, one FTE, just for building and maintaining this custom system. So add their salary, and the total might end up around $215,000 annually.
Wait, so the Kubernetes executor ends up almost the same price as GitHub hosted in this TCO?
In this rough calculation, yeah. The massive compute savings are offset by the high engineering costs for the custom solution. Now, the numbers change based on salaries, cloud costs, efficiency gains, but it highlights that the most efficient compute doesn't always mean the lowest total cost.
Fascinating. So based on that TCO, what's the strategic recommendation?
It really reinforces that hybrid architecture for this scale. Use GitHub-hosted larger runners for the absolutely critical, time-sensitive pipelines where paying the premium for speed and zero management is worth it. Then use ARC self-hosted runners, heavily leveraging spot instances for the bulk of your builds where you can trade a bit of queue time for significant cost savings. And implement that intelligent routing to send jobs to the right place based on their needs.
So the key insight isn't just pick the cheapest or pick the simplest.
Not at all. You should never optimize for just one single metric. The best, most sustainable solutions always find a balance. They balance cost efficiency with developer velocity, with operational sustainability. It's about using the right tool for the right job within your specific context.
That's a fantastic summary of a complex decision. It really drives home that this is about architecture and strategy, not just implementing a tool. So for you listening, whether you're prepping for that interview or facing the scale challenge in your actual job, understanding these trade-offs, the different philosophies, and these strategic approaches like hybrid models and phased rollouts, that's absolutely critical. It shows you're thinking beyond just the tech, right? You're thinking about the impact on the business, on the teams.
Exactly. And maybe the final thought is this. Beyond knowing the technical details, can you articulate the strategic value of these choices? Can you explain to a non-technical stakeholder why investing in ARC or building a custom executor or even paying for premium GitHub runners makes sense for their business goals? It's not just about the what, but the why. Why this approach helps the business move faster or save money strategically or reduce risk. That ability to connect infrastructure to business outcomes, that's what really distinguishes a senior engineer.
Couldn't agree more. That's the bigger picture. That's all for this topic. Stay tuned for the next DevOps Cloud interview question.